the stage is yours, Dirk.
Thank you, Pradeep. So this is joint work with Ben Brooks and Stephen Morris, and I think both of them are in the audience, so they can jump in if I get things wrong. The title of the paper is Search, Information and Prices. And what we're trying to do here is to see what we can say about how the distribution of prices are determined in a standard model of price competition for homogeneous goods. Now, economic theory suggests that if firms have common knowledge over the number of competing firms, then the predictions are very clear. Either we have a monopoly, and then with probability 1, the monopoly price prevails, or there are more than one competitor, so we are in an oligopoly. And prediction of theory is then that we simply have one price, and that price, at least the winning price, is the one that is equal to cost. In this sense, the model and the prediction is consistent, which is sometimes referred to a law of one price. But as Very and many others have observed, and actually more than 40 years, the law of one price is really not a law at all. Namely, price dispersion is ubiquitous and perhaps even more common today than it has been in earlier times. Since the observation that the law of one price is really not such a strong law at all, there's a large literature that has been developed that tries to explain equilibrium price dispersion and variance in the price as an equilibrium phenomenon. Theories that are consistent with the failure of the law of one price. An essential feature of many of these theories is that there is substantial uncertainty for the firms about the amount of competition, and in particular, that the firms don't have common knowledge about the number of prices that every particular consumer faces. And so this object, the number of prices and the uncertainty about our number of prices, will be a central part of our analysis. And we're going to refer to the number of prices that the consumer sees as the price count. We're going to try to develop two related issues that lead us then to the questions that this paper is going to address. Now, this literature, a very successful literature, has developed a lot of possible micro-foundations of how there might be uncertainty among competitors about the price count. Models of search are the ones that comes first to mind, but there are models of clearing houses, there's issues of advertising and attention, the issues of price discrimination, in particular spatial discrimination, that will all suggest that there is substantial price dispersion and that therefore the law of one price does not hold. The success and the multitude of all of these papers is in some sense also a curse. Namely, a priori, it's difficult to say which one of these many features that have been developed in the theory and these contributions is really the one that's empirically relevant. And often the parameters that identify or that describe the models are difficult to measure. So today we want to take a step back and simply to say, let's just fix a given distribution of the price count. Let's take that as a primitive of the model, and then think about, given that price count, what are possible distribution of prices, in particular possible distribution of sales prices that will support the revenue and the consumer surplus that might obtain in equilibrium. Okay. The second related issue that comes to bear on this question is that nearly all of these models, even though there are many of them, suppose that the firms have no information about the price count beyond what we might want to call the additional prior distribution about the possible number of competitors. Okay. Now, in static models or even in related dynamic models, the strong assumption about having no information is perhaps weaker than we might think, because in fact it turns out that whether the firms don't know anything or whether they know everything about the price count, so whether they have, in fact, perfect information, would not matter for the expected sales price. That is, there's sort of a small revenue equivalence result. Okay. And in fact, we'll show that either with zero information or with complete information, we have a lower bound in terms of what can happen in terms of the revenue that the firms get. But crucially and critically, there are a lot of possible outcomes in terms of revenue that can be attained for informational models that are in between zero information and complete information. And today we want to describe completely and extensively what are those possible outcomes are and describe them in terms of an upper bound and then in fact a much simpler lower bound about the revenues and the expected sales price distribution. Okay. So the results that I'm going to give to you today are essentially two. One is I'm going to give you a tight upper bound on what the equilibrium sales price distribution can be for any given fixed distribution on the price count. And then following from that, we're going to see that we can also describe of what a little bit of a little departure from perfect competition, so a small probability of there being a monopoly does in terms of the revenue. And in fact, what we find is that the marginal revenue, that is the derivative of the revenue as a function of the probability that there's simply one price, so that there's monopoly, is unbounded at or near perfect competition. Okay, so just a little bit uncertainty can go a long way in terms of raising the revenue of the competitors. Methodologically, that we are therefore giving complete and robust prediction about what can happen for the prices for a given fixed price count. And for the moment, or today at least, we're not talking about where the price count comes from. A leading application is perhaps you can think of this as sort of suggesting an empirical test to check whether there's collusion. Namely, for a given price count, we can ask, is the observed sales price within the bounds that we're going to derive? And if so, what we're effectively saying is that this price distribution can be rationalized by competitive behavior, though under private information. And if not, then we have a definite proof that at least the models can't explain such a high level of prices. Okay, so the two results that I want to focus are here. So unless there are immediate questions in terms of the purpose of the talk, let me jump ahead and immediately give you a very simple bare bones model that we're going to use to derive the results. Okay, so we're going to think about a single consumer who has unit demand for homogeneous good, and his value is going to be simply B. So there's no uncertainty about his value. The natural analogies with the continuum consumers, easily generalized results to downward sloping demand, but today let's just focus on that. There's a number of competitors with index N, and the production cost is 0. The consumer at any point in the market receives price quotes from a random subset, so that's where the uncertainty is. The uncertainty about competition is identified by this random subset of competitors who are actually quoting a price. And small k, the price count, is simply the cardinality of the set of firms that make a price offer. And what we're taking as part of the description of the model is that part of the primitive is the price count distribution mu that identifies how many quotes a consumer can get, ranging from 1, that's a monopoly, to n, which is the largest possible number of quotes. We're going to assume some symmetry so that for any given number, each firm is equally likely to be quoted. Okay, so the price count and the price count distribution are the new objects that are going to be critical for the analysis and that we're going to focus on. Okay. We said there's going to be uncertainty about the level of competition, and we're going to represent that uncertainty for the firms by means of a general information structure that gives each firm a signal and associated with each set of quoted firms, capital K, a joint distribution over those signals. Okay, so the interpretation that we have is simple. If a set of firms is quoted, then each quoted firm receives a signal that will convey some information about the strengths of the competition. And a firm which is outside of that set K, of course, doesn't receive a signal as it's not active. And the conditional probability distribution is then simply for even every given set of firms K, some conditional probability distribution over the signals. Okay, and we're going to want to think about what are predictions that will prevail, that will hold across all possible information structures.
Dirk, you don't have any dispersion type assumption on mu, or mu can be arbitrary?
Mu can be arbitrary. You know, it should be non-trivial. That is, it might have some probability on one and some probability on elements larger than one. Okay, good. And with this setup, we can then quickly identify what the strategies are and what the equilibrium is. This is, that is, for every signal, a firm chooses a price or possibly distribution of price. And today, we are always going to think about the upper cumulative distribution rather than the distribution, as this will help us visualize a lot of the results. Okay, so think about Fi as simply the probability that the firm I will offer a price that is larger than X, given the private information it has. And with this, we can then describe who is the winner, namely it's one of the firms that is quoted and that charges the lowest price, and we can identify the expected revenue. Now, this long formula looks complicated, but what it simply does, it tracks over all possible sets of quoting firms or possible private information, who is the winning bidder, that is, who is the winning firm that makes the lowest price, and identifies the revenue. And an equilibrium is simply a Bayes-Nash equilibrium that says that given the strategies of the other firms, I'm going to choose a best response. Yes? The object that we're going to try to keep track of is the sale price distribution. That's simply the distribution at which either an individual firm I is making a sale, given that there are K firms that have been quoted, okay? Or it is the unconditional distribution that is lower on the slide, that's simply averaging over all firms and over all possible number of quotes, the ex-ante distribution at which a sale happens. And the main question of the paper is going to be what equilibrium sale price distributions are consistent with a given distribution of the price count mu. Okay. So that was a very quick introduction, Amon, and now let's slow down a little bit and let me try to give you the main idea of the results and the construction of the results by means of a very simple example, and then highlight and indicate to you what generalizes and then state the main result. Yes? Okay. So we're going to start out with the simplest possible example, which is simply going to be the case of there being at most two firms. There's a probability that there's only one firm that makes an offer, and therefore mu is the probability that the price count is 1, and 1 minus mu is the probability that there are two offers. We're going to normalize the value simply to 1, so keep that in mind. And now I'm going to show 2 or 3 intermediate information structure to get you used to the concepts of sales distribution and see what information does to the distribution of prices, to then come eventually to the information structure that maximizes the sales price in the sense of first order stochastic dominance. Okay. So here we
Can I just interrupt for a second, since Pradeep may have stepped away? There's at least one question in the Q&A that I wonder if either Stephen or Ben wants to look at and sort of decide what to do with, either address it there or bring it to your attention at some point. So I'll delegate it to them if that's okay.
Wonderful. Thank you, Naveen. Okay, so here's a simple example. Let's start out with complete information. That is, the firms indeed know whether they find themselves in a competitive situation or in a monopoly situation. If it's a monopoly, then they will charge the maximum price at 1. If they find themselves in a competitive situation, then price is equal to marginal cost, which is equal to 0. What we find is the expected price is simply going to be the probability that there's a monopoly. And so the expected price, the revenue that the firms are accruing, is simply growing linearly in the probability of there being a single price count or monopoly. Okay. Here's the visualization of the sales price distribution. Okay, remember that we're going to look at the upper cumulative distribution. So we're starting at the blue dot at 1. The probability the sales price is equal or larger to 0 is 1. And then it drops precipitously, because if there's not competition, then the price is going to be 1, and it stays at 1/2 all the way up to 1. Okay. Suppose there were 0 information, so we're just having the prior distribution, that it's equally likely that we find ourselves a monopoly or an oligopoly. Well, then there's going to be a mixed strategy equilibrium, where the firms are going to be indifferent between trying to exploit being a monopolist, in which case they charge 1. So that's the left-hand side of the equation. That happens with equal probability to each one of them. Or they're going to try to price competitively, and that has to be resolved in a mixed strategy distribution that we can derive, and for which there's a support. Okay. Still, we can compute the expected sales price, and that has to be mu, because in equilibrium, the firms are going to be indifferent between trying to get the revenue that they would get if they were a monopolist and being more competitive. Okay, so visualizing this, we'll find that there's another sales price distribution now under no information. Okay. Now that shows that it has more dispersion. It therefore can't be ordered relatively to first order stochastic dominance. But important, in fact, these two extreme information structures lead to the same revenue. Okay. So now we are basically ready to think about what can additional information, what can intermediate information do to in some sense weaken the competition and raise the revenue of the firms. Okay. And an easiest or an intermediate step might be to think about partial information, but partial information that is still public among the competitors. Okay. So the matrix that you see below is simply the information structure that we're suggesting to analyze the situation. So either there's a monopoly, that is, there's just one firm, one or two that quoting, or we have indeed an oligopoly, and then the set K is 1 and 2. Okay. The signal that we're going to try to identify or label is now one we're saying, if you get your signal 1, you might be a monopolist, but I can't guarantee you that. Okay. So if indeed the state is such that there's only one price quote, then that means that I'm the firm that is active, firm R1 or 2. And in case there are 2 firms, it means that there's some uncertainty about whether indeed I'm a monopolist or that I compete. Okay. Still, that uncertainty allows us to raise the price, and in particular, allow the firm that got the signal that it's a potential monopolist to sometimes price at the full value, which is equal to 1, and otherwise render this. Okay. Let me just go back 1 second. How do we see that there's public information here? Well, if you look at the information structure that arises when there are 2 firms in the market, the one to the extreme right, the entries are on the diagonal, which means that both firms get the same signal, and hence they share the same information. There's public information. Okay. the monopolist has now a benefit. He's sort of informed that it's a good chance that he is alone, that allows him to raise his price. And in consequence, the known competitor is also becoming less aggressive because he thinks there's a good chance that he's actually facing somebody who thinks that they are a monopolist. In turn, we form an equilibrium where the expected sales price is higher. Namely, it's at least at the margin twice as high as it was before under zero or no information, under zero or complete information. Okay, so if you think about the marginal revenue, that now increases twice as fast in the probability of mu, the probability that there's a monopoly. Okay. The final example, to which I come now, but I'm giving you first the distribution of prices under this public information structure. Now you can see that the price distribution indeed stochastically dominates, okay, at least the no information price. Okay. Okay. Now we're going to push this even higher, and we're going to think about what are the prices that can be supported by some private information. Okay. With public information, essentially we forced the firms, even if there was some uncertainty whether they are a monopolist or not, to randomize over the same interval. With private information, we can, in some sense, relax that constraint and can have firms choose prices over different intervals. And that means that the firm that is more likely to be a monopolist can actually, on average, choose higher prices, and that then draws also all of the competitors to charge higher prices. Okay. So there's going to be an ordered support property that the person who's most likely the monopolist will always choose prices that are also relative to the support higher than the person who's less likely to be a monopolist, and that's the property that we will be able to show for general. Okay. So here's the last instance of the example. We're going to give or suggest the following information structure that you can see in the matrix. To the left, really not much has changed. It simply captured what happens if there's really just one competitor in the market. But to the right is what happens if indeed there are two competitors. You observe now, if you look at this matrix, that this is not a public signal anymore because they are entries of the diagonal, which means that firm 1 and firm 2 receive different signals, therefore have different pieces of information. There's private information in this environment. Before, the label, the type, could really be interpreted as a signal that says either firm 1 or firm 2 is a possible monopolist. Now, there's a different interpretation, but one that's significant in this model. Now, the private signal actually tells me or gives me a lower bound on the price count. Okay? Namely, if I receive signal 1 as firm 1, I know there might be either 1 or 2 firms in the market. However, if I receive the signal 2, I know for sure that there will be at least 2 firms in the market. Okay, and therefore I'm informed that I will be in a competitive situation. The elements of the diagonal tell you that that knowledge must not be common. That is, it could well be that the competitor is less sure whether he's a monopoly or not, but at least one of the firms basically has always a signal that not only gives a lower bound, but also gives an upper bound. Okay. We can construct an equilibrium of that sort that will again have a mass point if I get signal 1, and will have a random distribution if I get signal 2. But the key element here is that now we're going to be able to support a pricing strategy that allows the firm that got the good news in terms of the number of competitors, so the lower bound is 1, to price deterministically and always equal to the 1. And it's only the firms that receive the less optimistic signal, namely that the lower bound is 2, that will randomize. So now we have, in short, an ordered support property, namely the firm with the strong signal prices deterministically at 1. The other one will randomly price an interval that just sits below 1. Okay. In order for this to be in equilibrium, the diagonal entries can't be too large, and the exact determination is given in the formula. And in fact, the highest alpha that we can attain subject to the equilibrium constraint is in fact the equilibrium that maximizes the sales price, that gives us the highest revenue. Okay. I haven't given you the argument, but here I give you the visualization. That is, now we identified an information structure that gives us a higher distribution in the sense of first order stochastic dominance. So that means for every point X, the distribution that we have just identified, the ochre or orange color if you wish, has a upper cumulative distribution that sits higher and often strictly higher than all of the other distributions. Okay. So here you have a visualization what we mean by first order stochastic dominance. It simply means that the upper cumulative distribution is always higher, and now it's as higher than any of the other distributions that we have considered before. The second result can also now be given a visual interpretation, namely the expected price is now growing much more rapidly in the probability of monopoly, so we can compute what is the expected sale price. It's the same result that we got before for public information, except now we raise it. Remember, we are somewhere between 0 and 1. We raise it by taking the square root of it. Okay. Significantly now, we're going to think about taking the derivative at mu equal to 0. We see that actually the revenue increases very fast. That is, has infinite derivative at 0. That is just a little bit of monopoly, just a small probability of monopoly is in fact allowing us to create equilibria that look very different from the competitive situation. Even though on average, we have competition. Okay, so these are the two results visually represented now. Perhaps I'm going to give you an idea of how we're going about obtaining these results, improving these results for the much more general model, and what's the structure and the idea behind the proof. Yeah? Okay, good. Okay, so the main result is that, in fact, the construction I just offered for 2 will hold for arbitrary price count distribution, and that we can construct an information structure that dominates, in the sense of first order stochastic dominance, any other information structure, public or private. The key features of the construction that generalizes is that when the price count is 1, we're going to maintain, even under uncertainty, the possibility that the monopoly price is charged. In fact, it's going to be charged deterministically. The signals will have the interpretation that they will represent information about what the lower bound of the price count is. Okay, and the adjoint equilibrium will have the property that the pricing of the types will have an ordered support property, namely firms that have a lower bound on the number of price counts will price higher. Firms that have a higher price quote as a lower bound will charge lower, therefore more competitively. So that generalizes the idea of nested market that came up earlier in the public signals. And the final observation is that just as in the two-firm signal, the equilibrium strategy has amazing property that, in fact, across all of these supports, the equilibrium will have the property that the firm, while choosing a price, will at the same time be indifferent between any lower price that is also in the entire support of the price distribution. Okay, so I'll have roughly 10 minutes, so let me give you a few ideas about the construction, a formal statement of the theorem, and maybe some visualizations.
Dirk, just a small question. So what you had simplified in the example was only the number of firms, or was there anything else that you?
No,
that
was the only thing. Yeah, and,
okay.
and of course we just looked at a small number of possible information structures. We didn't make any claim as to what are the possible information structures.
Right. Thanks.
Okay, good, great. So what does the upper bound look like, and how are we going to generalize it? Okay, so we're going to be in a world now where we have a fixed price count distribution that simply tells us the prior probability of the number of competitors. Okay? And we're going to associate to each to these price count distribution a support along which there will be prices that are also labeled according to the number of competitors. Okay, so a person who gets a signal that the lower bound is 1 will price between x0 and x1. A person who got a lower bound that it's 2 will price between 1 and 2, and so on. Okay. The cutoffs and the distribution are going to be completely determined from the expected number of quotes. So this is the primitive of the model was the quote distribution that gives us an expected number of quotes between 1 and any arbitrary number of m. And this information then allows us both to determine the thresholds as well as a candidate equilibrium distribution or a candidate sales price distribution. Okay, so what you notice, what we're describing here is just the sales price distribution in the aggregate. That is, you don't see an index I. It is just an aggregate distribution of what the revenue of the firms will be, or at least the candidate. Okay.
So, sorry, Dirk, can you state, have you stated formally the assumptions on mu and on the signaling? What are the assumptions for the theorem?
We have a finite support here. So for any arbitrary finite support, we're going to compute an upper bound. And in terms of the information structure, we just have weak measurability conditions. So there are, almost no further assumptions necessary.
Okay.
Okay. So now we're ready. We basically have given a candidate sales price distribution that's as upper bar that I constructed you just from the primitives of the model. Okay. And the claim is that once we have given any fixed price count distribution mu, then any information structure T, so subject to the weak measurability conditions, okay, and any equilibrium that's associated with this information structure and is consistent, that is projects down to the same price count distribution. The equilibrium distribution of those sales prices must be first order stochastically dominated by the candidate as upper bar that I just gave. Okay. And as you notice, the as upper bar was just constructed in terms of the price count distribution, so it didn't have any information. The second part of the theorem is then that indeed we can find an information structure and an equilibrium associated with that information structure such that what results as sales price distribution is the as upper bar. Okay. How are we going to get to the proofs? Well, it's natural to expect that there might be an upper bound on the sales price distribution, right? Because if sales prices were too high, if, for example, they were all trying to price at the monopoly level, then clearly there would be incentives to undercut and gain more sales. Okay? So this suggests there might be non-trivial bounds on how high the sales price distribution go, in particular on how high in terms of first order stochastic dominance. It also suggests that the relevant constraints are those associated with cutting the prices. Okay, that is, I'm going to try to push the price distribution as high as possible. And then what should happen is that I'm trying to do that up to the point where the downward deviations are going to start binding. Now, which ones might be binding? That is hard because remember, we have an arbitrary type space. We're thinking about mixed strategy equilibrium, though the space of deviation is potentially very large. Okay. We're going to, in some sense, relax the constraints and going to look at just a small class of deviations, those that we call uniform downward deviations. That will give us necessary condition on how the bounds on the equilibrium sales price distribution must look like. And then we're going to show that, in fact, those conditions that come from the relaxed constraints can be attained by an information structure.
So, it's 9 minutes left.
Yes?
Okay.
Absolutely. Okay, good. So the key idea here is to consider just a small class of deviation, okay, where we're thinking about in the information structure and in the equilibrium, a firm who were to choose a price X is in fact choosing a price PI, is in fact choosing not PI but rather X. Okay. So that's a uniform downward deviation because for any price that it would have chosen according to equilibrium, we asked the firm to consider what revenue it would have gotten if it were to lower the price to a uniform lower bound, which is X. Okay. That is a deviation, a well-defined deviation. And that deviation will give us the above inequality, integral inequality, which basically links the equilibrium sales price distribution for any number of sales codes, so the conditional sales price distribution, to the aggregate sales price distribution, which simply aggregates over all possible number of codes. Okay. So this is a necessary condition for equilibrium. Okay. But what we can show is that, in fact, the sales price distribution that I gave you as a construction before, the S upper bar, is in fact a sales price distribution that maximizes this inequality pointwise. And not only that, it holds this pointwise at an equality condition. Okay. And it has the property of ordered supports. That was the second part of the construction. Okay. And so we can solve now basically the systems of first order differential equations inductively on the number of price codes that are being observed. Let me give you a visualization to see how this works. Okay, so we're thinking about a uniform price count between 1 and 5. The candidate equilibrium sales price distribution as upper bar on in terms of conditional terms is being displayed here, right? So what you see is that conditional on the signal, that is the lower bound on the price distribution, each one of those have a different support. These supports are ordered, that is, they're going down in the number of price counts. So they're going down as the environment is likely to be more competitive. And each one of them form a conditional price distribution. Okay, so that's the construction of the candidate, okay, and that shares the ordered support property. Okay. And what's the information structure that attains that, or that supports, that gives the agent the information that is necessary in order to generate the equilibrium price distribution, and in particular the equilibrium sales price distribution. Well, that can also be given in terms of the original price counts. Namely, we're going to draw for every profile K a candidate signal, one for each agent. Okay, and that candidate signal is literally a lower bound, a sharp lower bound on the number of price counts that are going to prevail in market. We're only choosing that according to distribution, the details of which I don't have time to go into. That's alpha of L conditional on K. Okay. And this distribution is such that at least one of the firms, possibly many, know the, in fact many, and for those, the lower bound coincides with the upper bound on the price quotes. So they know for sure what the true number of quotes in the markets are. Okay. If we put these things together, the information structure and the equilibrium pricing strategy, then what I'm displaying you here now is what the aggregate, the prior distribution of sales prices look like in the market. And so what I'm varying here is the total number of competitors. Okay, and what you see is that as we increase the number of competitors and as we maintain otherwise a uniform distribution, so the markets become more and more competitive, the distribution converges more and more towards the low price. Okay, so here there's also a stochastic dominance relationship that is work. What you see basically as the funny kinks within each distribution is simply a manifestation of the ordered supports, where we move from one support to the other. So at those points, the density doesn't have to be, or the distribution doesn't have, it's continuous, but it's obviously not differential. Okay. I think with this, I should probably end. I presented you two results today, one on the equilibrium price distribution and one on the revenue impact of monopoly. Okay. The paper actually has many more additional results. In particular, we are very much interested to see to what extent our results not only hold for static models, say of search, but for sequential models of search where the firms get the information sequentially. In fact, our information structure sort of naturally supports such a sequential search. Okay, but let me stop here.
Okay, we have time for questions. I don't see any in Q&A, but are there questions that others want to ask?
Yeah, well, I've got one. So Dirk, so I guess the main result basically says that, so you characterize a distribution such that any other distribution of sale prices must be first order stochastically dominated by that distribution.
Yeah.
Do you know that sort of any distribution that is first order stochastically dominated can be obtained with some information structure?
Not any, right? So let me just go back perhaps to this picture. Okay, so let me try to give you an answer by means of this picture. This picture is basically giving you an upper bound, that is the maximum distribution, that's the orange distribution. Okay, there is also a lower bound, except that the lower bound is not unique in the sense that either zero information or complete information give you the lowest expected sales price. But in turn, these two distributions and many others cannot be ordered according to first order stochastic dominance. So that there's a unique highest distribution, but in some sense, there are many lowest distribution. Now, it's relatively easy to see that essentially any distribution that can obtain from a convex distribution between the maximum and any smallest distribution you pick can also arise as an equilibrium, because you could simply get that from convex combinations of the two underlying information structures.
I think
And that's a complete characterization of all the distributions, or is there? It's not.
I
immediate
hesitate to say complete, because you know, I mentioned that the lower bound, there is not a unique distribution, so there are many. I'm not sure that I, for example, could give you, at least I can't give you right now, a complete and exhaustive description of all the distributions that could attain the lowest expected sales price.
Okay,
The two that you see are examples, but I don't think they're exhaustive.